Hello friends, today we start with ninth unit of our syllabus, chapter 14, titled as Semiconductor and Electronic Devices. What is the strategy involved? Here is the mind map. This chapter is divided into two parts. First part is semiconductors and the second part is electronic devices. Now first we take up first part, semiconductors. In semiconductors we will discuss about energy bands in solids, semiconductors, doping, p-n junction. In second part, electronic devices, we will study about junction diode and applications, photonic devices, transistor and its applications, and logic circuits. So this is our strategy, how we are going to learn about this chapter. Now we take up one by one. First topic we take up formation of energy bands in solids. Now to understand formation of energy bands in solids, we are to first learn about energy level. Then we are to learn about energy bands. Then we will come to formation of energy bands in solids. Now what is an energy level? Let us define. Various stationary orbits of an atom corresponding to some definite energies are known as energy levels. I repeat, various stationary orbits of an atom corresponding to some definite energies are known as energy levels. Energy of a level in an atom is given by the expression En equal to minus 13.6 into Z square by N square electron volts, where Z is atomic number of the element and N is the number of orbit, which is equal to 1, 2, 3 or N, or you can say principal quantum number, and represents corresponding energy level. For N equal to 1, E1, that is first energy level, is equal to minus 13.6 electron volts for hydrogen atom, because for hydrogen atom Z is equal to 1. Now look at this diagram. This is a diagram of an atom where this is first orbit N equal to 1, this is second orbit N equal to 2. For first orbit it is K level and for second orbit it is L level. And here you can see potential energy curve of an atom. For N equal to 1 it is K level, for N equal to 2 it is L level, for N equal to 3 it is M level. Okay, so these are energy levels: K energy level, L energy level, M energy level, corresponding to a particular orbit, N equal to 1, N equal to 2, N equal to 3 respectively. This is how we have the understanding of energy levels. Now energy bands. How we define energy band? Large number of discrete but closely spaced energy levels are defined as energy bands. I repeat, large number of discrete but closely spaced energy levels are defined as energy bands. Now suppose three atoms are brought together to form a solid. These are three atoms which we have brought close to each other to form a solid. Then 3 K levels corresponding to n equal to 1 will form band, and L levels corresponding to n equal to 2 will form another energy band. So this is energy band corresponding to K levels, and this is energy band corresponding to L levels. Okay. This is how we develop the concept of energy bands. That is, large number of discrete but closely spaced energy levels are defined as energy bands. Here there are 3 atoms, so we have 3 K levels which are closely spaced because atoms have come very close to each other when they are in the shape of the solid. And similarly, we have 3 L levels which are close to each other and they form energy bands. So there is a energy band corresponding to K levels, there is energy band corresponding to L levels. Okay. Now, formation of energy bands in solids. When number of atoms are brought together to form a solid, the energy levels of original system get deformed continuously and emerge out in the form of energy bands. Number of energy levels in individual atoms is equal to number of energy levels in the group of atoms forming solid. That is, n individual is equal to n group. Isolated atoms has well defined energy levels. When atoms are brought together to form a solid, energy levels are modified. This modification is not appreciable in case of inner shells, but considerable in outermost shells of the atoms. It is because these are the electrons of outermost shells which are shared by more than one atom when they come closer to form a crystal. Now we come to formation of energy bands in solids with special reference to silicon. Now silicon atomic number is 14. It means there are 14 electrons distributed in various shells. How these electrons are distributed in various shells, let us see. 1s2, that is 2 electron in 1s shell. 2s2 means 2 electrons in 2s shell. 2p6, that is 6 electrons in 2p shell. 3s2, 2 electrons in 3s shell, and 3p2, 2 electrons in 3p shell. 1 electron in 3px and one level remains empty. 1 electron in 3py, again one level remains empty, and no electron in 3pz, that is 2 levels are empty. So this is how electrons are distributed in various shells of silicon. Now look at this diagram carefully. X-axis we show spacing between atoms and y-axis we show energy. And these horizontal lines show various shells. This is 1s shell which contains 2 electrons. This is 2s shell which contains 2 electrons. This is 2p shell which contains 6 electrons. It is 3s shell which contains 2 electrons, and it is 3p shell which contains 2 electrons as per electronic configuration, of course. Now consider outermost orbit of silicon. The available energy levels are equal to 8, out of which 4 are filled and 4 are unfilled. The filled levels are 3s2, 2 levels of 3s and 2 levels of 3p. So 4 levels are empty, because if we write configuration, then we will write it as 3s2 3p6, but only 4 electrons are available. So 4 electrons can occupy the space and 4 remains empty, because there are no other 4 electrons which can occupy the empty spaces. So in the outermost shell we are left with only 4 electrons. So 4 electrons will occupy their place. So total number of available energy levels in outermost orbit are 8. Now let us look at filled and unfilled energy levels. Since available energy levels are 8, the filled levels are 4, 2 of 3s2, 1 of 3px and 1 of 3py. Now unfilled levels are equal to 4, 1 of 3px, 1 of 3py and 2 of 3pz. Now when n atoms of silicon are brought together to form a solid, then 8n levels of outermost shell interact, get modified and spread out in the form of energy bands as shown in diagram. Now inner shells 1s2, 2s2, 2p6 are hardly affected. That is, these levels are hardly affected. It is outermost shell which have appreciable modification in energy distribution. Now formation of energy bands. How formation of energy bands takes place in silicon. Now when spacing between atoms is OD, this is point O and this is point D, atoms are far apart and each atom has well defined energy levels. Second, when spacing between atoms is OC, this is C point, atoms are brought near to form a solid. Interaction between outermost energy levels start. These are outermost energy levels. Third, when spacing is further reduced and is equal to OB, this is B point, 8 n energy levels are continuously distributed and cannot be identified as which are filled and which are unfilled levels. Now here 8 n energy levels are continuously distributed and it is difficult to identify which are filled levels and which are unfilled levels. Okay. Now fourth step, when spacing is equal to lattice spacing OA. So this is O point and this is A point. So the atoms are very near to each other now. When spacing is equal to lattice spacing OA, then it forms a solid. Energy levels spread out in the form of energy bands. 4n filled energy levels form valence band and 4n unfilled energy levels form conduction band. The energy gap between valence band and conduction band is known as forbidden band. This is how the formation of energy bands takes place. Now look at the diagram. When spacing between atoms is equal to lattice spacing, Then you mark these points for valence band and these points for conduction band, and the gap is forbidden band, and the gap between the two is forbidden band. So this is how formation of energy bands takes place in silicon. In the same way we can deal with the other elements also. Now let us define energy bands, valence band, conduction band and forbidden band. First we define valence band. Now this is energy band diagram. You look at this diagram carefully. CFS means completely filled states, which are inner states. Valence band and conduction band are produced due to interaction between the electrons in the outermost shell, since inner states are completely filled states. Okay. Now let us define valence band. The band of energy occupied by valence electrons is defined as valence band. I repeat, the band of energy occupied by valence electrons is defined as valence band. This band may be completely filled or partially filled. Now let us define conduction band. The next higher permitted band to valence band is defined as conduction band. I repeat, the next higher permitted band to valence band is defined as conduction band. This band may be empty or partially filled with electrons. Electrons in this band move freely and are called as free electrons. Now, forbidden band. The band of energy between valence band and conduction band is defined as forbidden band. I repeat, the band of energy between valence band and conduction band is defined as forbidden band. The energy difference between valence band and conduction band is called as energy gap and is expressed as Eg is equal to ECB minus EVB, and it is equal to Hc by lambda. I repeat, Eg, that is energy gap, is equal to energy of conduction band minus energy of valence band, and it is equal to Hc by lambda, where H is Planck's constant and lambda is the wavelength of light emitted when electron jumps from conduction band to valence band. Okay. Now let us classify materials on the basis of energy band diagram. Materials are classified into three categories. Number 1, conductors. Number 2, semiconductors. Number 3, insulators or dielectrics. Now these are the energy band diagrams shown before you. This is for conductors, this is for semiconductors, and this is for insulators. Now here in this diagram you can see valence band, conduction band overlap. Here you can see valence band, conduction band gap is very small, and here you can see valence band, conduction band gap is very large, and accordingly we tabulate their properties. Now look at this table. This column is for conductors, this is for semiconductors, and this is for insulators or dielectrics. Now first, in conductors, valence band and conduction band overlap. In semiconductors, valence band and conduction band do not overlap. In insulators or dielectrics, valence band and conduction band are separated far apart. Second point, energy gap between valence band and conduction band is 0 in case of conductors, and energy gap between valence band and conduction band is approximately equal to 1 electron volt in case of semiconductors, and energy gap between valence band and conduction band in case of insulators or dielectric is very large and is of the order of 6 to 9 electron volts. Okay, so this way we compare the two properties of conductors, semiconductors and insulators. Assignment 14 continues. Question number 1, define energy levels. Question number 2, define energy bands. Explain formation of energy bands in solids. Question number 3, define energy bands. Explain formation of energy bands in solids with special reference to silicon. Question number 4, define the following: valence band, conduction band, forbidden band. Question number 5, identify semiconductor, conductor and insulators from the following energy band diagrams. Question number 6, energy gap between valence band and conduction band for conductor, semiconductor and insulators are given by EC, ES and EI respectively. Arrange them in ascending order. Number 2, descending order. Question number 7, the energy gap between valence band and conduction band of a material is 1.21 electron volt. Calculate wavelength of radiation emitted when an electron jumps from conduction band to valence band. Thank you so much. Next time we'll take up second part of it, semiconductors. Till then, goodbye and good luck to you.